Okay, now part 4, I think that gave people a little bit of trouble, right? And it's because it's a different kind of question. It's a show question. And show questions are always interesting because you get the answer. How do you actually go about giving the answer then, right? First of all, let's break down what this means. I should say that there are actually 2 ways that curves can kind of increase, right? So this curve, if you sketch it out, it looks something like this, right? So graphically, you could see that it's always increasing. That's not really a proof, though. Okay, it doesn't really show anything. Another way that curves can increase is that if you have a cubic, the difference between these two, I don't know if anyone can see it, it's pretty subtle. Like, if you look at this point over here, what do you reckon the gradient would be? It'd be 0, right? So technically, the curve isn't, they're going to use a word in your textbook called monotonically increasing. It's just like a fancy word for like always, right, basically. Yeah, they kind of mean the same thing. So if it's the gradient of 0, at that point, it's technically not increasing. It's like the same sort of gradient, right, same value. So when it's monotonically increasing, this always has to be greater than 0, basically. And so we know that from this question that we're really looking for derivatives, right? So we've got f dash of x is equal to 3x squared plus 1. And we basically want to see that this is always increasing or always greater than 0. Alora, do you reckon this will be always greater than 0?
Yes.
Why?
It's squared.
Okay, so there's some intuition about how this works, right? Like, hey, something squared plus 1, or something squared multiplied by 3, then add 1, right? If you just took something squared, like, it doesn't matter what value you put in there. You can put in 1, you can put in -1, you can put in 0. This will always be greater than 0. I guess the question is kind of how do you show that? It's probably not quite enough to just say, yeah, therefore f dash of x is greater than 0. I think we can do a bit more than that, right? A few ways you can sort of approach it. Basically, firstly, what is this curve? It's a parabola, right? And it's a concave up parabola, and what would it look like? It would look like this. So 3x squared, that's like a vertical dilation, and then we're shifting up 1. I'm just trying to sneak in the language there, so. Right? So that's what it looks like. Is this always positive? This is always above the x-axis. Remember, when I mean positive now, I'm looking for, okay, what are the values I'm going to get? Well, it's all the values up here, and it's all above the x-axis. All of these here, I should probably do f dash of x, right? All of these are going to give me positive values, right? So this is how I know that's always going to be positive. Since f dash of x is always above the x-axis, f dash of x is always greater than 0, right? So it's recognizing the connection between, okay, this is my graph, actually it's this one. This is my graph, and this is the gradient function. And as long as this is always above the x-axis, the gradient function, then it's always going to be positive, okay? So therefore, f dash of x is always increasing. There was another way to do it. Matt, what did you do? Yeah, so I thought that was an interesting approach. So you may remember back from year 11, there was something called the discriminant. And it basically tells you how many roots an equation has, how many intercepts. And if you found the discriminant of this expression, because it's a concave up parabola, and if we find the discriminant, which was b squared minus 4ac, all right, so what's it? 0, yeah, 0 squared minus 4 times 1 times 1, 3 times 1, sorry, negative 12, right? If the discriminant is negative, this is kind of like, hey, why are the negative things going on? Well, if the discriminant is negative, it means that there's no x-intercepts, right? So that's another way you could have done it, but just showing you there's a few different approaches to this type of question. And knowing like all the different tools available for you is going to be really helpful. Cool. Questions about that? So I quite like this one because you just have to know how to draw it, and you can explain it quite nicely, but discriminant is also a great way. I didn't even think of that, actually. Okay, this, again, kind of interesting when we have to sort of explain things going on. Firstly, find f of 0 and f of 1. So notice we're going back to the original function now, right? So find what f of 0 is and find what f of 1 is. Anyone got that for me? -1. So respectively, f of 0 is, yeah, and f of 1 is 1. So what does that kind of imply, right? If you're testing these x values, and we've got a change in a sign there for the y values, What's the implication there?
The x-intercept's in there somewhere.
Yeah, right, because, and I'm cheating because I have the graph, right? But if f of 0 is -1, and f of 1, let's say is over here, that's 1, right? Logically, the x-intercept has to be somewhere in between there because you're going from a negative y value to a positive y value. So obviously the graph is crossing the x-axis at some point. But there's a bit more than that. We have to explain why it only has one x-intercept. Where am I going to get that from?
Well, I know that it's in there, right? And then the graph's always increasing.
Exactly. So usually these two parts are sort of related to each other, right? The first thing is we showed that it was always increasing. So the gradient's always going to be positive. And then the next thing here is that we've shown here, there must be an x-intercept between these 2 points, right? And so if you put these two pieces together, what happens is, okay, it has to always be increasing. It's going to cross through here at some point, and it's going to keep going up forever. There's no way it can come back down and have another y-intercept or anything like that, okay? Sorry, another x-intercept. There must be an x-intercept between x equals to 0 and 1. And it is the only one, I guess. Just write a little sentence about it. Didn't quite get to do this one. I will let you try that one yourselves. Just to finish this guy off, so last question. Show that this curve has no stationary points. So same idea, right? Like for stationary points, we're already thinking about like derivatives. We can draw the graph as well. You may not be familiar with this one. But this looks, like what does this look similar to? It looks kind of similar to a hyperbola. And a hyperbola, well, that looks like this. And if you're squaring it, basically, you're taking all the like negative values, you're going to make them positive, and you're going to make these values slightly change as well, but the general shape will look like this actually, with some values that are changed. So obviously there's no stationary points that are occurring here because the gradient's always going to be either always increasing or it's always decreasing this way, and there are asymptotes here. But let's go about this from a calculus perspective, right? Because if I take f of x, and I write it like so. Not a very helpful way to differentiate. That's why we prefer the index notation. I'll write it as x to the power minus 2. That way, now when I take the derivative, that's just going to be, I'll drop the power down, so negative 2, x, subtract 1 from the power, so negative 3. Now what? Well, another way you could write this is negative 2 on x cubed. There are actually no solutions for something like this so that this is going to equal to 0. So if we want to solve this, that's equal to 0 for stationary points. Right. If I want to say negative 2 on x cubed equal to 0. Right, there are actually no solutions, right? Because there's no value of x here that you can make this equal to 0, right? If you try 0, it's going to be undefined. If you try any other value, it's going to get a fraction. So, therefore, there are no solutions. And f of x has no stationary points. Okay, so that's how you can go and show that something doesn't have stationary points. Essentially, we try and solve an equation. It can't be solved. And we lay it out in that way. And I think, there's a probably logical implication with this one. We don't have to really expand too much about it. It's pretty clear there are no solutions for that equation there. I guess the other way you could do it is you could say that this guy here, if you knew what he looked like a hyperbola with a negative value over here. We're actually going to have asymptotes at x equals to 0 here. So there's no value that exists where x equals 0, there's an asymptote, so you could sort of justify it graphically as well. That's another way you could approach answering this.